It's cool? Hey, how are you? All right, so it's time. Thank you for coming from this talk. I'm really happy to be, well, it's not really back at CodeBits. It's like a new iteration, but I was thrilled when Celso kind of tweeted that he was thinking about bringing back CodeBits. I was kind of jumped on Twitter and said, I want to help, and I'm really happy that this came true. So today I am going to talk about building machine learning products, namely some secrets or takeaways that I've learned throughout my experience doing this that you could take away if you want to incorporate machine learning into your own products or actually launch successful machine learning products. I am António Alegria. I am product lead for Feedzai's cloud software as a service solution for fraud prevention in electronic commerce. So basically, we have a product in the cloud that is protecting some of the top brands in the world that have online stores and that they want to know when they ship something that it's not going to be shipped to someone who stole your card. Because when that happens, actually, it's curious. It's not the bank that's going to pay you back the money. The merchant is going to pay you back the money online. So we're there to protect the merchants. So how do we stop a robbery? That is the big question that we need to think about and that we're trying to solve. How do we stop people from stealing money from you, stealing money from merchants, stealing money from banks? I know that banks don't get much love nowadays, but stealing people from the common folk, from people creating their own businesses online is not great. And so we do this, and Feedzai does this, and I do this by arming the good guys. And I think Iron Man, apart from being a very cool superhero, represents the kind of approach we like to use for machine learning. We use machine learning as kind of a weapon, kind of a bodysuit that helps businesses and helps humans and helps other tools to achieve a goal you have. It's not something that completely automatically does whatever it thinks. It's not something that takes over your whole business. It's an enhancement and a very powerful one. So how do you build a machine? And how do you do this in a scalable way? And how do you do this if you want to start your own project? So I'm going to talk about things that you can do that do not require a team of scientists, that do not require a team of PhDs, that do not require a team of more than one. This is something you can start doing on your own, playing with machine learning in a way that actually does something useful. So just to clarify, because the title is a bit broad and these subjects can go very deep and very broad as well. So this talk is about some tips, some secrets, some things that I know that work that you can use to build a successful machine learning product. One in particular that can be used in multiple use cases. So not something that you can just train on some data and use it for a very narrow use case, but something that you could provide to different clients with different needs, with different business models, with different data, okay? And that's a big challenge. And also, I'm focusing here on structured data problems as well. I also focus on the challenges of doing this in a software as a service scenario, in a software as a service paradigm where you can be receiving new clients every day, clients for which you don't really have a project team on site asking them questions and stopping for 8 weeks to build a perfect model for them or to help them integrate with your system. So it's something a very low-touch product that should just work. This has to do as well, I'm going to talk about data API design choices. How can you design a data API for your machine learning-based product that works for these kinds of scenarios and is successful? And also just in general, how can you take advantage in a scalable way to the data that you receive? Lots of businesses today and lots of startups, they use as their business model or their call to fame, we're just gathering a whole bunch of data. In the future, we'll figure out something to do with that. But in the end, a lot of them can't really leverage this data, and they really don't know how to do this. And this is also something I'm going to talk about, how you can today, even with tools you have, open source tools or off-the-shelf tools, you can start doing this and leveraging data that you're receiving from your clients. This talk is not about, machine learning now. Something that is really being talked about is natural language processing and structured data problems that use deep learning, like self-driving cars, virtual assistants, all of that. This is not going to be the subject of this talk. I'm not going to go into specific technologies. I'm going more in terms of methodologies and philosophy. I can mention some technologies that can help you achieve some of these things and implement some of these things, but that's not the focus of this talk. And I'm also not going to focus on data visualization or UI, although this is a very important part of a data-driven product. So when I talk about machine learning products, I can give some examples that you guys know very well, that you deal with day to day. Gmail spam detection is kind of the textbook example of a very simple, very useful, just works machine learning product where you just press a button and the system learns. And before you know it, with everybody using Gmail, you're benefiting from the data that you're also providing to the system. Recommendations that you have from Amazon, that you have from Netflix, that you have from dating sites. These also are a good example of machine learning products that are key to the service these products are providing. Amazon, for example, has now started using machine learning to automate access controls. Instead of going through a bureaucracy, you can have a system that learns from information from the people, from the time of day, from their behavior, whether to give access to a certain person or not, predicting heart attacks, and of course fraud detection, which is what Feedzai currently does. But what makes these products, or some machine learning products, good? So obviously they do their job very well. This means that they can predict with a high accuracy, they can learn immediately when you give feedback, and you don't really think about them being there. They just blend into the environment, they blend into the service, or they blend into your life, right? So it's something that, one thing that artificial intelligence and machine learning struggled with in the beginning was that it was very in your face. So it worked, it was often that it didn't work. So you always had to think about, so the system hasn't still learned this, and what you want is something that you don't even think about that it's there. Also, they have the ability to self-evolve. And this is important not only from a user's perspective, you want it to give feedback and the system to learn, but also from the developer and from the maintainer's perspective. You want the system to be able to evolve by itself without having to do, a new sprint and a new project just to get the system to get better and better. You'll do that, but the system should be able, on its own, to learn and to improve and to self-correct. In the end, good machine learning products seem magical. You don't configure anything, you just send data, and it works. And you get that fuzzy feeling when the system where you were previously used to something that had errors, maybe you had to configure a bunch of rules, you had to configure a bunch of policies. From one day to the other, it just starts doing what you want without you having to tell them much and learning from other people as well. So I mentioned Feedzai and I mentioned fraud detection previously, and I'm going to just talk to you a little bit about what we do so you can have context. So Feedzai, as a company, has a product that focuses on detecting fraudulent payments in digital commerce. And this can be from whenever you go to a store and you swipe your credit card, within a few milliseconds, Feedzai is analyzing your transaction, is comparing it conceptually to all past transactions you've ever made, to all transactions that anybody has ever made. It's comparing with a database of patterns is seen from fraudsters and from legitimate people, and it's going to say, hey, I think this card has been stolen, and this is not being done by António or by João. This is fraud. So you're going to flag that, and the bank is going to block that. That's one perspective. Another perspective is on the merchant side, for example, where, as I said, if you're an online merchant, in particular online commerce, or if you're an Uber, or if you're a Cabify, or if you're one of those online services, all transactions done online, the liability, if you do with a credit card, is on the merchant. So if someone steals your card, goes to Amazon, buys a Mac or buys 10 Macs, and Amazon approves that, and the bank approves that because the bank doesn't know, then you will see in your receipt for your card, hey, I didn't do this. I'm going to call my bank. You call your bank, and your bank is going to call the merchant's bank and say, give me back the money. This is not a legitimate transaction. So Amazon loses the money on those 10 MacBooks, and it loses the MacBooks. So this is a huge problem for online merchants. And Feedzai also has a product that is more focused, is more offered on a software as a service paradigm, because merchants don't have that whole bureaucratic structure of banks that want to have things in their data center. They just want something that works. And their Feedzai basically receives transactions via an API, receives behavior data like the customer logged in, the customer made a review, the customer added items to a cart. We continuously update profiles on every customer, every card, every device, every entity you can imagine. We just build these continuous profiles that codify the behavior of these entities and the relationships between these entities. And then we give this all to a machine learning model that learned from this data, and then we continuously update to learn from this data, and it will tell us the likelihood of it being fraud. Okay? Also, something that we do that is very interesting is the ability to give human-readable explanations. So we don't just give a score or a probability saying 60% chance this is fraud. We actually tell you why we think this is fraud. It's because this card has been used by 3 different customers. This guy has used 3 devices in 1 hour. What's going on? So look at this, and merchants can call the customer and ask about this. Oh, I see that you're trying to buy these MacBooks, and you've been using these 3 devices. What's going on? And say, oh, I'm having trouble logging in and whatnot. So maybe it can do a validation with more information on our side. And Feedzai is an interesting case because you're dealing with financial data, and it's huge data. And Feedzai currently is working with the top payment processor in the world, and is processing $2 billion per day. And this is, at the end of the year, this ends up being 3 times Portugal's GDP that we're looking at, and we're securing. And we're saying, hey, don't let this go through. This is a bad guy. This guy is good. We're securing commerce that way. And we're doing it across the globe. We're in several different geographies. And one particular thing, since we're dealing with financial transactions, we don't want to introduce friction in the process. We don't want, merchants, banks don't want you to wait 1 more second, 500 milliseconds more to wait for your purchase to finish, because you just go away. You're just going to, oh, this is too much. I'm just going to the other guy. So we need to do decisions in a very, very short time window. And for example, when you do ADM transactions or you go to a store, a physical store, and you buy, we actually have a window of 25 milliseconds to do all of this analysis, all of this comparison, look at your profile, look at everybody's profile, and come up with a decision. Otherwise, they will just go through, they won't wait on us, they go through with the transaction and they risk it. So, just giving it a brief overview, especially and in particular to our cloud product, which I'm working on and which I helped develop. We have a REST API through which we receive payment transactions like purchase a MacBook, and actions like login, review item, view page, things like that. We receive all of these things into a request, and we go through a bunch of high-level steps. First one, we enrich the data. So if we have an IP address, we go to external providers or databases we have internally, and we see, is this IP address a proxy? Where is this IP from? Is this from Brazil? Is this from Portugal? Is it US? Is this IP part of a known malware network? Or, for example, we can check if the card, where's the card from? What's the country of the card? Things like that. So we add more data than we received. Then we go through this, what we call one-to-one profiling and analytics, where we track all of past transactions, we track a bunch of metrics, we correlate entities together, see which things are related to one another, so that we have more data about the transactions. And then we feed it to a machine learning model, and in the end we have also a layer of human-built decision rules and detection rules that taking advantage of the information from the model, they can make different decisions and they can establish different policies. Maybe because for certain products, you want to have a stricter attitude. For other products, you just want to take more risk, maybe. And so we give you the ability to customize your risk profile according to that. So it's not just machine learning and do what you want. As I was saying, we give these human-readable explanations that we extract directly from the machine learning model. And this is crucial because the problem sometimes with using machine learning model is that they are very good at learning patterns that are very complex and that humans couldn't possibly in useful time come up with, because they look at data and they can see if country is Portugal and amount above 20 and time of day is between noon and 1 p.m. and the product category is shoes and this and this and that. So very complex patterns that humans, for them to do that, we have to do a multivariate analysis that would be huge. Then you don't understand the model, and you risk not understanding what your system is doing. But we are able to extract from the score of the model, from the probability that it's fraud, why the model thought this was risky or why the model thought this was legitimate. And we give you the two sides of the decision. We give you why the model might think this is risky, and we give you why the model might think this is legitimate. Because typically we have very gray area decisions, so we need to give that information as well. The main challenges that we have, in particular in this cloud product, is that, so this is software as a service. We don't have a project team in clients configuring everything and tuning everything for each client, so it should be a system that just works out of the box. The scenario we're dealing with, although we're talking about purchases and we're talking about online commerce, the actual breadth of use cases is huge. You could be dealing with clients that are online stores, that are shoe stores, very specific. You could be dealing with Amazons. They sell everything. You could be dealing with marketplaces like eBay. You could be dealing with an Uber or a transportation company. You could be dealing with a services company, I don't know, lawyers or something like that. So you could be dealing with very different services with very different business models. So if you're dealing with an online gaming company, they sell digital goods. And digital goods, you either approve them when you buy or you don't. You don't like click buy and then you have to wait for a day for them to ship the digital good to you, right? If it's a physical good, you have to wait for shipping, so the clients have some time to review manually the transaction. So although we give this probability of fraud, right? We say this transaction has a 60% chance of being fraud. We can define in the system, if the probability of fraud is too high, just auto-decline it. If it's low enough, auto-approve it. If it's a gray area, it's between 60 and 70, I don't really know, this could be fraud, could be not. I'm not willing to just auto-block it. I could be blocking a good customer that just likes to buy a lot of shoes. I'm going to send it for review. And since I'm going to ship it, I have to wait for the transportation company to come. I have time, maybe hours or even a day, to look at the information, maybe call the customer and validate things. You don't have that in digital goods situations. You don't have that with Uber. Uber either takes your ride or it doesn't, right? So that's a big challenge. And it also can involve different abuse scenarios. I'm talking about stolen credit cards, but in our clients, they don't just want to deal with these things. They want to deal with account takeovers. So someone is actually taking over your account, your credentials, or maybe employee abuse. We have clients that have employee programs where employees can have discounts. And they want to make sure that their employees aren't abusing their benefits or giving their accounts to other people. So you might be dealing with different use cases that might require different training methods and different models to kind of detect them, right? And in the end, these kinds of generic solutions need to scale. And I've used scale a bunch of times here, and it's the title of the talk, and everybody talks about a scale. But when I talk about scale, I'm actually not very concerned about performance and big data and distributed processing and things like that. To me, scale is about the ability for a small team to handle an increasing amount of clients that come in. And they don't need to double the team if they have double the clients. And they don't need to double their operations team if they have double the clients. So it's the ability for you to handle an increasing client load an increasing number of scenarios, different scenarios you're handling, an increasing complexity of the kinds of analysis you're doing without just spending linear amounts of money. And performance, of course, is related to this, but when I mean scale, I mean this kind of ability to do this. So, after saying all of this, let's go over a few of what I believe to be some very key components of a good machine learning product. One of them, as I was saying, is the data API. So this is the interface, and this will dictate what kind of data you have and what's the effort you have from transforming that data into useful information for your models and useful knowledge for your users. So one thing that I think is very useful to approach these is a framework that I call the Data API Specificity Spectrum. That's a mouthful. And this slide is very busy, I know. Just focus on the middle part. So data APIs are generally a trade-off between a very high flexibility, where your clients can just send anything. They can send data in what way they want. They can send, even if it's structured, even if it's just a key value pair. They can send, no, this shoe store is going to send the shoe size as a number, and the other shoe store is going to send the size as a character, a string, or a letter. And this customer is going to send me the amount in dollars, and the other customer is going to send me the amount in cents. So you could have all of this flexibility, and that is good because clients can send exactly and all information that they have without losing anything in translation. So they just send everything as they have and what they have. The problem with this is that it makes your job very, very hard to create a scalable, again, data processing pipeline and machine learning pipeline that is able to deal with tens, hundreds, thousands of clients, each of them sending different things with unclear semantics, right? At the other end of the spectrum, you can have a very use case specific API, where you have a very well-defined language, you have a very well-defined set of fields, you have very strict validations for those fields, but you don't let any other customization go there. This is good in a sense because it helps your clients know what they need to do to integrate with your system, but they probably will leave a lot of information out because it just doesn't fit, or it's too much effort for them to even think, how am I going to fit this information in your API? The good thing about these kinds of APIs is that since the data is so normalized, it's hugely scalable. I mean, you can leverage data from everyone very easily to create a single model. You can share data between clients very easily. Your data processing pipeline is very uniform. You can make very strong assumptions on the things you receive. And your feature engineering and data analysis work is very easy because everything is the same. At the middle, and as always, in the middle, well, I don't know how to say this in English, but the virtue is in the middle, perhaps, I don't know. You can have kind of this middle ground where you have a very well-defined language. In this case, for Feedzai, would be a very well-defined language for commerce. You have things like amounts, you have things like currencies, you have things like shopping cart with product ID and what's the cost of the product. You have things like shipping address, you have things like IP address, very well-defined things that most commerce, most shops, most services will need to use, but you can also have a leeway to let them customize what they send. This is done usually by supporting custom fields. So you can support in your API a slot when they send a request where you can put a key value pairs with whatever data you want. And you can even make this very, very flexible, or you can give a little bit of structure to this, maybe saying you can indicate what's the data type of this, and maybe you can indicate what's the type of thing you're sending. Is this like a currency item? Is this kind of a category? What are the possible values? You can kind of go between. This is kind of a spectrum, right? So it's not a discrete thing, but this has the ability for you to reuse data and create shared models, but also allows you to tailor models for different clients or for different segments. So you could group shoe stores and have a model for them. You can group marketplaces have a model for them. You can group transportation companies have a model for them. And you have this flexibility, and I think this is the way to go. So have a very well-defined language, and your native fields should be very well-defined with very clear semantics, but also open the gates for some customization. Also regarding, this was more about sending requests. Regarding the responses you give back to the client, one of the things you need here, and we're talking about a classification problem, I don't think I mentioned this before, where we're sending probability, which is what I call the score. You also should have 3 more things. You should have a decision. This is, you should approve, you should decline, you should accept. Of course, this decision could be based solely on the score, so you don't really need it. But clients typically want you to give them a recommendation. Some clients will not use it. Some clients will use this recommendation. Also, you should have human-readable explanations. Again, this is so that you can give some transparency as to what the model is doing. This is important because, especially when clients start out, they don't yet trust your model. They don't trust your machine learning. So you're going to tell them, this is 90% chance it's fraud. And they either trust you blindly or they want to know why. And these explanations are very useful for that. Also useful for you to debug your system. And the third extra thing you should have is similar to the explanations, but these are machine-readable, what we call reason codes. This is so you can give some hints as to what kind of decision was this or what kind of use case. So you can put in these reason codes, I recommend declining this because this is employee abuse and because this, we detected a high velocity, for example. So very simple labels you can put there that the client, if they want to do some kind of, give different responses to their customers, maybe if it's a low-risk thing or it's because they're abusing their employee benefits or they're doing very fast transactions, they're going to give one message. If it's a certain different kind of risk, they're going to give another message. So having this kind of thorough response and information is very important as well. Just to give you an example of what we do with our API, and this is a very trivial example and it's a very trimmed down one. For requests, you can send things like user ID, amount, the items, etc. And there, as you see in blue, you have the user-defined fields. And this is important, again, let me reiterate this. If you have a shoe store, you either add to your API every possible use case you can deal with, or shoe stores or new businesses might have some interesting data points that you didn't think were important for your API, like the shoe size, that they want to send. Shoe size is very indicative of fraud because fraudsters use stolen cards to buy goods that they then resell. And they want to buy shoes with sizes that will have maximum value in the black market. So maybe knowing that is important to you as well. And for the response, again, we have the score, we have the decision, we have the reason codes, and we have the human-readable explanations as well. So this was the data API. Now let's talk, I'm talking about machine learning, let's talk about actual machine learning algorithms. But just in 30 seconds because actually this doesn't matter as much as you might think it does. So if you're dealing with machine learning, I just suggest you to encapsulate the machine learning part into its own component that has a very clear interface. It receives a feature vector, it receives what we call an instance, and it outputs a score, and it might output explanations and reason codes, but that's it. And you encapsulate that, you test it, you make sure it's great. You can choose whatever algorithm you want, but then you focus on the other parts of the systems because that's what matters. I can tell you that if you're starting out, I recommend starting with an algorithm that is fast and easy to train, it's fast to evaluate, it's very easy to, it's an algorithm, it should be an algorithm that gives you good performance without much tuning. So there are lots of algorithms where you can tune a bunch of hyperparameters. Don't go there when you start. It should support classification and regression as well, because I think as your use cases evolve, you might want to do both. And it should be white box. So it should be easy for you to inspect it if you need it. I recommend you use and consider random forests, gradient boosting machines. I think deep learning is very, very interesting, but I think it's still not there in terms of performance, in terms of speed. It's not there in terms of ease of use. You will need to have a much higher hardware overhead to do deep learning properly. It's very heavyweight to train. And it's still not clear, although it promises saving you some work in terms of feature engineering, for structured problems, it's still not clear if you, in the end, you will probably still need to do feature engineering. I think so. For starters, just keep to random forests or GBMs, boosted trees, and I think you'll be great. If you look at Kaggle challenges for unstructured problems, deep learning wins everything. But for structured problems, typically you see these two algorithms as the main ones. So machine learning is actually 90% data processing. So all of the effort I think you will have to have a successful machine learning product is, and by the way, I'm sure that my colleagues at work are doing, they told me they were going to do a drinking game with every time I repeated a word, and I think I said machine learning like 50 times. I will stop. I will call it artificial intelligence now. This is 90% data processing. And let's think about a concrete pipeline for data processing and for ML. So you have your historical data, which you need. If you want to train a model, you need to have some data to train it on. If we look at the bottom part of the screen, this is the training part. So basically, you have this data. These are your transactions, or these are your dating site profile information, or whatever. You go through a data processing pipeline where you can enrich the data, you can filter it, you can transform it, you can aggregate it, you can project it, and you end up with what we call an instance vector, plus these little squares, which are the class, which in the fraud scenario, green would be not fraud, red would be fraud. And I will go back here, just to give an example of input data we might be talking about. You have amount, currency, user ID, device, etc. And the features, and just to clarify, when we say features, these are the variables you will have in the instance vector that you'll feed to the machine learning model. You could have things like the amount. This is a good feature. It's a very common feature to use. Could have time of day. This is a transformed feature from the timestamp. You could have day of week, again, transformation. You could have if an IP is from the same country as the store, so if it's a foreigner doing the shopping. And you can have a bunch of features. By the way, these red features don't do that. And I see lots of people starting out using these kinds of things as features. Don't do that. This is going to give you very bad results. And basically, the model is just going to learn which devices, which users are bad, but it's not going to learn what are the underlying patterns that will allow it to detect new bad users, new bad devices, and things like that, right? So this is just an example of a simple thing you could do here that you would have here. Then you give this to the algorithm does its magic, it's a black box, and then you can use this model in production, right? You're receiving your live input data through your API, you're applying ideally the same transformations. This should be the same, and I'm going to talk a bit about this. You'll get the same kinds of instance vectors. You won't have the labels. This is happening live. You will have to predict them. You give it to your algorithm, and it will classify it and give you not very certain, it'll give you like a gradient of whether this is fraud or not fraud. And then you can check if this is actually correct, if in a week or 2 weeks you receive information that transaction was fraud or not. So taking that into account and taking those features into account, this model is not going to be very good because it cannot distinguish with those features a transaction from different people but with the same amount, the same IP, country, same time of day. And this can be very different people. One can be a real big scammer and the other one an angel. So the goal we should have, and this is key, and I think it's one of the main parts of this talk, is that the model must see the current event. So it should see the transaction flowing in and all of the information, but it should be able to use as well all of the past events that ever happened, and all for that customer or for that device or for that card, and also all past events for that are related. So everything. So ideally, as a goal, conceptually, the machine learning model, when receiving an instance vector, that instance vector should have all of the information that your product has ever seen. Of course, this doesn't work like that, but that's the goal. And a good approximation to achieve this is to use what we call, again, going back to a favorite buzzword, the one-to-one profiles. So a profile is basically a summarization or an aggregation of historical data or of a window of data. And it's basically, if you have a credit card or you have a user account, you will be doing transactions over time. And if I took those transactions and calculated some metrics like, what's the number of transactions that this person does per day? What's the average? What's the standard deviation? What were the last 5 products he bought? So all of these aggregations and summarizations of all of your history is what we call a profile. So these are some examples. And we call it one-to-one because classically in the market, products would do these profiles by segment. So they wouldn't do João's profile and credit card A's profile and IPB's profile. They would do young man profile. So young men usually do an average of 24 transactions a day. And so when a transaction comes in from you, oh, this is a young man. Let me get the profile for this young man, and I'm going to give this to the model. No, we want to do this per person, per device, per everything, per each entity, and per groups of entities. So the profile is applied over usually time window. Windows could be sliding, could be tumbling, and they could even be delayed. And you also have entities to group by. So this, and if you think about data processing scenarios, the time window is the slice of data you're going to use for this aggregation. The entities you group by is going to be what you put in the group by expression, group by card and user. And then you have an aggregation function like a count. The challenges that we usually find when trying to use this kind of approach are that you need to find a way to calculate all of these profiles for these thousands or millions of different entities in real time, because if you have an attack going on, if you have someone doing 1 transaction a second, you can't update its profile 1 hour after it happened. You will lose him. So you need to be able to calculate them instantly and update them instantly to use them and for them to be useful. You need to be able to pair short-term profiles, like last hour, last day, last 5 minutes, with long-term profiles, like 6 months, 1 year, lifetime. So you can compare what has João been doing in the past year versus what is he doing now. Is his average today different from his usual behavior from the past year or not? Another big challenge that as you start doing these more complex features is how do you guarantee that what you're doing here, what you're doing here is the same you're doing there. Because now you're dealing with time-sensitive calculations. You need to have the events in the same order. You need to make sure that when you say 5 minutes window, you're going to simulate a 5-minute window here, not with the wall clock, but with the event stream clock. So that's the challenge you have there. And so another thing is, if you want to make sure that what you do in training reproduce what you do online and live, you need to ensure that your data scientists are able to implement these and ship them directly to production or ship them to the release team. Classically, and in a lot of companies nowadays that do machine learning, you have the data scientists and you have the developers. And the data scientists, they look at the data, they use R or they use Python, and they come up with these features and they test them. This is great, we're going to have an amazing performance. Here, developers, here is what you need to do. This is the spec. And then developers have to implement it. And this takes weeks or months to update a model. But who guarantees that the spec is actually well implemented? So it's really key that data scientists can implement it directly and can ship it directly. So it's kind of data scientists being DevOps, but dev data scientists. So again, reproducibility between training and production is essential. This is, to me, the most important thing. You need to ensure, if you're working with machine learning and if you have a machine learning-based product, this is the thing that will kill your product and kill your metrics if you don't have it. And without making sure that the code and the process and the way you write the features is the same in training and in production, without ensuring that you can actually ship exactly what you're using in training to production, you're going to introduce risk that there will be differences. Even if you have a very complex, slow process of QA and testing, you won't be able to iterate then on adding new features, adding new models, okay? And not having this reproducibility, this can introduce what we call a concept drift. That basically means that what you gave your model to train, what he learned from, is not the same he's going to see in reality. So if he's learning from something that is not the same as reality, it's probably not going to make a very good decision, right? This is the same thing as if you learn to do a job in Portugal and you go to do the same job, maybe a taxi driver, for example. You're a taxi driver in Lisbon, you're great. You go to, I don't know, you go to Tokyo or you go to Turkey, you probably won't be able to do a good job. You don't have the learning experience. The reality is different from what you trained on. So, again, reiterating this. And how do we achieve this holy grail of having the ability to do all of these fancy features and having the ability to easily have data scientists code them and having the ability to ship them directly to production, and then, on top of this, to be able to do this in a way that scales and handles lots of new clients, handles lots of new requirements, and handles huge loads of data. So the way to do this, and the way I recommend this, is bringing back a technology that was on the rise maybe 5 years ago, called complex event processing. Now, probably nobody talks about it, and it has been, I think, absorbed by data processing tools that you might find. Maybe Apache Flink, maybe Spark also has a bit of this, Storm has a bit of this, Scalding as well. All of these data processing tools that have been commoditized have integrated a lot of the concepts that complex event processing introduced. And complex event processing should be paired also with a large-scale, what they call big data platforms like Spark or Hadoop or whatever. So just to explain very quickly what this is a methodology and a family of technologies that was focused on allowing you to make sense of huge streams of events, be it transactions, be it user actions and whatnot, and be able to process them in real time, in streaming, correlate them, and come up with higher level insights from that data instead of just making decisions based on that specific event. So it gives you the tools to do exactly what I talked about for the profiles. And it typically relies on a DSL, similar to SQL, that flips the paradigm of data processing, at least that there existed at the time, and still that is not as widespread as I would hope, which is classically you have your queries or you have your data processing logic and you apply it to data that is at rest. And what CEP does is you have your logic, you have your queries in memory, and data goes through them, and it updates state, it updates metrics, it creates new events, and allows you to do these kinds of things. As an example, this is a pseudo DSL for CEP engine, where you could write a very similar thing to SQL, but you are able to use time windows, and you can do things like calculate for each user and card, what's the average amount in the last 24 hours, what are the number of transactions, what is the velocity, and you can do this in a very easy to use way. And data scientists can do this very easily. It's easy to learn, it's easy to reproduce, and it's easy to test. CEP operations that are common go through filtering, correlation, windowing, transformations, all of the things you might want to do with multiple streams of events and multiple streams of events you want to correlate and analyze and associate and aggregate, you can do with these kinds of tools. The problem with CEP technologies, and I think this is why they didn't really kind of go mainstream, they didn't really become one of those things you hear in CodeBits or in Pixels Camp in every other talk. So React, there's kind of 5 talks about React, 5 talks about machine learning. The reason why CEP didn't become one of those buzzwords is that it was very reliant on in-memory processing. And if you rely on in-memory processing, you can only handle up to a certain level of volume, right? And so to be able to handle long-term profiles, so 6 months aggregations, or even to be able to handle very large clients, very large scenarios where you have thousands or millions of transactions per second, which you can't really keep in memory without a high cost, The way to really take advantage of this is not say this is bad. CEP is very useful, but pair it with a high-scale distributed processing framework, like pair it with Spark, pair it with Hadoop. Hadoop is a little bit old right now, long in the tooth. Spark is the cool thing, but pair it with Spark. Spark already has some streaming capabilities, has some of these operations, but the DSL, I think, is not there, and the full range of capabilities is not there. So I think if you look at some of these tools, some of these technologies, and pair them and try to see how you can use it together with other kinds of things that do things more in batch, you will have a very, very powerful platform to build your pipeline on. And you should be able to build something that you can use in training. You run your DSL in training, and you take the same DSL, you put it in production, and it should just work. And then you have the ability to do code reviews, you have the ability to have data scientists ship code and ship the models. So we're kind of running a little bit out of time. And so I'm going to focus on just a few tips, a few extra tips I have on top of API design and on top of what kinds of algorithms you should use, in terms of on top of having some kind of philosophy for data processing and for reproducibility. First of them is you really should strive to support deployments of new models working in the background, not affecting your decisions, not affecting your clients, but working in the background without any downtime, so that you can more quickly iterate and test things and check that things work in production. Not in the lab, not with historical data, in production, with transactions today. You have something that if you want to flip a switch and put it in production, live, scoring things, you can do it very easily because it's already there. So this is a really important thing. Another thing we learned is that having good, consistent data, again, related to having the same kind of data you have in historical data with the live data, and sometimes you have a new user, and the user has a database of data, but they typically don't store everything they see in real time, right? They store some things they don't store, or they don't store the intermediate states between an order, because an order can be created, and then it can be updated and can be canceled, and maybe in the database they just store the final state. This poses a problem to you, because if you want to keep the training part exactly the same as production, you will need to use the smallest common denominator, the least common denominator, in your training features. You won't be able to use all of the data you're receiving in production. You will have to limit yourself to the data you have in your database and that you have in production. Because if you don't do that, you will risk a concept drift and the model is not going to perform well. Also, let's say that you have a new user, you received a bunch of data in a CSV, it's incomplete, you'll have to use that to train an initial model, fine, but then in production you will see lots of new data. It will be very, very quick that the production data you have, as long as you have labels saying it's fraud or not, you should start using that very soon instead of using the historical data. And even if you have an historical data, a huge volume, if the data is more consistent with what you have in production, it's better to have less data. Even if it's significantly less data, your model is going to be better than if you use a lot of data that is inconsistent between itself. Something that is not very intuitive is you should do things that do not scale. So we have all of these platforms, we can do all of these things for free, processing data, doing huge complex things. We can use machine learning to just automate pretty much everything. But you should actually go in, open the data, look at specific rows, open the CSVs, look at specific data fields. This doesn't scale. You can probably do 10 of them in an hour, perhaps, to do it well. But I guarantee you that you will always find good insights. You will either find things that you didn't predict that will help you create new features. You will find maybe bugs or problems in your model, things that your model is not picking up. So always take the time to do these kinds of things that do not scale. Go into the database, do some queries, test some things manually. And that will bring you a huge benefit, maybe more than people typically assume. Also, something that is very very, very not intuitive is throwing away good data. You should do this. And I think a couple of talks behind, Miguel from Feedzai also talked about this. And the reason to do this, especially if you have a use case similar to what Feedzai is working on, which is fraud, is that fraud is a really unbalanced use case. This means that in all of your transactions, a great majority of them will not be fraud. So you're actually looking at a needle in a haystack. If you give data like this to a machine learning algorithm, most likely than not, it's going to learn some things, but probably it's just going to say for most of them, this is not fraud. Why? Because if you actually have a model that says nothing is fraud, you will be right 99.5% of the times. This is a huge accuracy. And accuracy is one of the used metrics in measuring machine learning, which you cannot use in some of these use cases. So for you to enable your models to actually learn the underlying patterns, it's better that you drop good transactions, you undersample them, and you create a smaller data set where you have maybe a 9-to-1 proportion or a 50-to-50 proportion on the transactions. And you should do this randomly. Of course, you need to do this not on your input data. You need to do this on your instance vectors after you did all of the profiles and all of your processing, because if you do this before, you will lose information, you will lose a number of transactions, things like that. So do this before you train the model. Don't do this on your test data. Just do this before you train your model so it can actually learn what are the underlying patterns. So the key takeaways I would like you to go away from this talk is design APIs with very well-defined language, but with openness to support custom fields and perhaps custom events as well. Focus on the data processing pipeline. Make sure that it's reproducible instead of focusing a lot on the machine learning algorithms. A lot of people, when they approach a machine learning problem, they spend time testing 10 different algorithms. Oh, this is what I'm going to do. I'm going to put all of these fields. I'm going to put device ID as a feature and IP, and I'm just going to test SVMs and random forests and XGBoost and all of that, and I'm going to see what's the best. This is a waste of your time. Of course, there will be a time where you will want to win 1% or 5%, and that's the good time to really focus on tuning your algorithm. But if you go with the ones I suggested, you'll be good to go. Just focus on your data processing pipeline. That's where your value is going to come from. Look at CEP technologies. Look at event stream processing technologies and think about how you can pair them with distributed data processing, batch processing frameworks. And in the end as well, don't just rely on machine learning. Also rely on human knowledge. This can be based on you go down and looking at the data. It can be also having rules, the ability to put some human-created rules in the system to either decide maybe different thresholds for the model based on the amount, or even to establish some policies outright that you know that if the model has a problem, at least you'll be covered by this insurance policy that you put there. So don't just put all your eggs in the machine learning basket. So this was the talk. Definitely, if you have any questions, I will be open to receiving them. And if you want to be a data samurai, if you want to join a team of people who are doing very, very ambitious things, a team of people who are trying to do the impossible sometimes, and working on the bleeding edge of very tough problems, and creating real impact in our clients, in our customers, and on businesses, join us, come talk to us in our booth, take a look at our website, let me know if you need to talk. I will be accepting questions now if we still have time. I've heard there were very, very low density of questions in other talks, so please indulge me and ask anything. It can even be unrelated to the talk. It can be about Feedzai, it can be about anything. Please. Yes.
Hi.
Hey.
Basically, what I want to know is what's your stack at Feedzai and why you chose that stack?
When you talk about stack, actually, I should have had a slide with the kind of technologies we're using. Okay, so I can tell you we're very focused on JVM based languages. So we use Scala, in particular in our cloud product. We use Java as well. We use Spark. We use so for the CEP engines and a lot of the things we do in terms of data processing, we have our in-house built technology, right? But we use Spark, we use React on the front end, we use Docker, we use, I don't know, Diego, do you want to add something? That's good, right? I don't know. For the machine learning algorithms, we actually implement them ourselves. It doesn't mean we don't read the papers for random forest or whatever we're using, but we actually sometimes implement ourselves so we can tune some things to have some power over that. But yeah, I think those are kind of the main pieces we use. RabbitMQ, things like that. Oh, we use Cassandra as well. Yeah.
I have two questions.
Sure.
So you guys do fraud transaction and detection, supposedly, in real time, right?
Yeah.
So if you guys are doing it in real time, why did you focus on using Spark, which is supposedly used for mini and batch processing, instead of something like Aaron or Flink or something that's more focused on real time? And my second question is, since you guys have confidential on your slides, are we allowed to talk about it out of here?
Yeah, I was thinking about that. That's just a template, man. I'm sorry. Yeah. Yes, the real-time part, we're using Spark and we're leveraging as it's evolving. But we've been doing this even before Spark existed. And we have our own homegrown data processing engine that does stream processing and does stream processing at scale. And when we're now doing this, we're also leveraging Spark for what Spark does well, which is for some of the more heavyweight distributed data processing things. But when we're doing that together with our own data processing engine in-house, which is tuned for real time. And it was built, an important thing about our engine, it was built specifically to be able to be replayable offline. So you can pipe in historical data, and it will not use the wall time, it will use the time of the events. So you can actually completely replay and reproduce what you would see in a live system offline with stale data. Come on. 3 questions. Let's go for the third. Huh? Última? Okay, last question. Who wants to take the last question? Crickets. All right. Thank you guys for attending.